Good morning. Thank you for the introduction, Praveen. My name is Amreen Fatima, and I'm a doctoral student from Texas A&M University. Today, I will be presenting the topic of structural design, analysis, and full-scale testing of ultra-high performance concrete girders. This research would not have been possible without the contribution of the following people. This is a TxDOT-funded project led by Dr. Husty. We were mainly interested in identifying the potential utilization of ultra-high performance concrete in standard Texas highway bridge girders. What you see here are the finished cast-in-place deck slab and the UHPC girders, Specimen 1 and Specimen 2 in the field. First, we had to conduct a design feasibility study to identify target properties that would best optimize UHPC design for bridge girders when compared to conventional concrete girders. Having identified those properties, we had to achieve those using by developing a non-proprietary UHPC mix, and then conduct material level and full-scale tests on specimens developed from that mix. This is UHPC specimen being poured, and that's the final product. Ultra-high performance concrete has several benefits, such as high compressive strength, high tensile strength, coupled with superior durability. This gives the advantages of getting longer spans, fewer girder lines due to higher prestressing force, and the long-term benefit of longer service life. This justifies the high initial cost of UHPC. Frequent maintenance and inspection of bridge girders in Texas costs TxDOT a lot of money. Therefore, it is having a longer service life would really help with the better life of these structures and reduction in maintenance and inspections. We developed a non-proprietary UHPC from locally sourced materials in Texas. This effort was led by my project mate, Young-Ki Hong. And since commercial UHPC is very expensive, it was necessary to develop a locally sourced material mix design so that the cost can be cut down. We tested that developed mix in the precast plant. And once we were happy with the trial batch, we then fabricated UHPC girders at a full-scale level, and we had cast-in-place deck slab poured on top of it in the laboratory. We then tested the performance of these specimens in the lab under flexure and shear. To give an overview of the mix developed at Texas A&M University, we got high early strengths of 12 KSI at release, and about 18 to 19 KSI at a later stage. A modulus of elasticity of about 6,500 KSI and a tensile strength of 0.625 KSI. I would like to point out that we were using 1.5% fibers by volume when compared to the usual 2%. This also reduced the cost. We got a high flexural tensile strength of about 2 KSI. We cast two 50-footer long full-scale specimens. The first one was with 30 strands, which were all straight, and we got a prototype design of 77 feet span length with this one. And the second one was with 38 strands, and we had 6 strands hard. And this specimen had a prototype length of 85 feet. One thing we were interested in identifying was the shear performance of UHPC because of the steel fibers. The steel fibers drive the cost of the mix by about 50%, and therefore we were interested in identifying the potential of reducing the transverse web reinforcement in these girders due to the higher shear performance of UHPC. What we did was have one half of the girders with minimum transverse reinforcement by design, and the other half was without any transverse reinforcement. Since we had a conventional concrete deck slab on the top, and we wanted to maintain composite action at the interface of UHPC and the CC deck, we provided shorter U composite bars at the interface. We provided bars of number 5, which were just shorter version of the standard R bars, number 4, used in Texas. The first specimen was tested and we got a pretty good capacity of 5,400 cubic feet in flexure. The first specimen was designed for a lab tensile strength of 0.7 KSI. However, for the companion field specimen, we found out that the tensile strength was 0.55 KSI. Therefore, we were anticipating shear crack prior to flexure failure, and that is what we got at the no web reinforced end. In order to preserve the beam for flexure, we decided to unload one actuator nearer to the no web reinforced end and went ahead and loaded the other end until we got flexure failure. You can see the cracks under, and the failure occurred under the loaded actuator. All the predictions were very close to the experimental values. The second specimen had better tensile strength of 0.625 KSI, and we had higher shear capacity due to hopped tendons and more prestressing. Therefore, we did not run into any issue of premature shear crack with this specimen. We conducted the 4-point bending test until we got the flexure failure under one of the actuators, and we got a higher capacity of 6,400 cubic feet for this test. Then we wanted to check the shear capacity of the minimum web reinforced end of the first specimen, and we conducted shear tests with span by depth ratio of 2.36 for all, and higher than 2 for almost all of the shear tests. You can see the shear cracks that were developed at that shorter span that we tested, and we had narrow cracks at the west end, and then we had wider cracking at the east end because this end was already more damaged due to the previous flexure test. The next specimen was, as I mentioned before, was stronger in tension and had better shear performance with about 444 kips shear strength. We did not run into any issues of premature shear cracking, and therefore, after the flexure test was done, we tested the whole beam under shear, and sure enough, the end with no web reinforcement failed first under shear, and we observed typical web shear cracks in this region. Along with that, we had interface slip at the bottom flange, and a prestressing strand was exposed. Then we wanted to test the minimum web reinforced end of that specimen. So we again tested the shorter span, and we got similar web shear cracking for this specimen as well. And we had a pretty high shear capacity for this specimen of about 550 kips, which was pretty close to the predicted values. We can compare the performance of the two girders. Here in this plot, the purple bars denote the flexure demand, and the blue bars denote the service demands. The green bars denote the capacity of both the girders, and we can see under flexure, both girders performed exceedingly well when compared to the service and the factor demands. For the shear test, the striped green bar is the no web reinforced end, and the solid green bar is the minimum web reinforced end. As I mentioned earlier, the first specimen had slightly lower tensile strength and all straight strands with lower pre-stressing, and that can be reflected in the performance of the no web reinforced end being ever so slightly higher than the factored shear demand. However, the transverse bars provide better resistance in this specimen. For the second specimen with higher tensile strength, more pre-stressing and hopped tendons, we have more contribution to shear, and that is easily reflected from the better shear performance of both the ends when compared to the factor demands. The cracking was also very limited, and under service condition, we got no cracks. Beyond the factor demands, we observed slight hairline cracking at failure, we only had major cracks at the crack localization areas with a 4.5 mm crack and 3 mm crack for the two girders respectively at the soffit where the crack occurred. For the no web reinforced end, we observed wider cracks under shear with a more crack opening near the failure. For the minimum web reinforced ends, we had quite narrow cracks until the major crack opening. From the experiments conducted, the following conclusions can be drawn. The girders can be designed for UHPC using the standard code provisions with slight modifications for UHPC. The first principles of mechanics hold good for identifying the behavior of UHPC girders with conventional concrete deck slabs. Using standard constitutive relationships, stress strain models, and a sectional analysis gave us good agreement with the predicted results and the experimental results. It was seen that the shear strength is highly dependent on the tensile strength of UHPC from the experimental results. The flexure performance was kind of governed by the composite action with the conventional concrete deck slab on the top and the UHPC girder being mainly engaged in tensile strength at the bottom. The crack bridging properties of the fibers was very effective in getting ductile behavior. The cracking was shown that the performance of the girders under service conditions was really good with no cracking and mainly hairline cracks beyond factored load. We noticed one additional thing for the second specimen. Near the failure load, we observed an initial slip at the interface of the cast-in-place deck slab with the UHPC girder. The shear performance of these girders also showed great potential for reducing the minimum web reinforcement in these girders, and that would in fact make the design more efficient in terms of time and money. The crack bridging properties of the fibers tend to delay the onset of a shear failure. Cracking again was not visible during the service conditions, and beyond factored loading, we had more cracks being observed. Major conclusion that we drew is that increase in tensile strength, harping of strands, and higher prestressing force tends to largely improve the shear capacity of the girders even without minimum web reinforcement. Having minimum steel in the shear region will definitely enhance the ductility of the specimens. This is an ongoing research, and we are processing the data to get more analysis out of these experiments, and we will be fabricating a longer and a bigger specimen to continue the tests. Thank you very much, and I would also like to thank the sponsor for their support.
Hi, excellent presentation, very concise, good information. I just have one kind of detail question. So for the U-bars that you use to establish composite behavior, and in particularly in the area where there was no shear reinforcement, what was the length of embedment? And related to that, you mentioned something about slip. Was there a difference between the two? How much composite action did you maintain?
Okay, that is a very interesting question. Thank you. Yes, this is a very interesting topic, the interface between the UHPC with other materials, and not a lot of research has been conducted in this area. We are also looking into it more carefully. To answer your first question, the U composite bars were about 12 inches long with an embedment length of around 6 inches within the concrete. And incidentally, we had the slip at the end with the other bars as well. Like it wasn't on the end that you would expect intuitively that would occur at the one without it. So it could be because there wasn't any surface preparation on this specimen, and there was on the previous specimen. So that would be the first guess, since surface preparation of UHPC is very important because of not having any coarse aggregate, so that aggregate interlock advantage is missing. And therefore, I would That would be my guess, but we would make a solid conclusion after further processing of the data. Thank you.